Yeah, rough draft is due Thursday. I'd like to see a rough draft of your discussion section.
And in the format, you can find it on Piazza, right?
The format can be any format because, well, it depends. If you do more than that, I'm going to post something on Piazza. I forgot to do that, but you want to focus on the discussion section because that's the most time-consuming section to write. You know, the discussion section is going to be like you're just trying to explain what's happening in the synthesis. And that is, explain it in a way that's different than the procedure or what we call the experimental section. In the experimental section, you're just mixing different amounts of chemicals. This would be equivalent to like when you're baking, say, bread, and you have to mix this much baking soda with this much flour or whatever else. And so when you're doing a recipe, you aren't really thinking of what is the purpose of adding the baking soda. And so in your discussion section, you don't have to say, you know, you took this many grams of potassium dichromate, this many grams of oxalic acid, mix it with this much water. You can leave out those details. And so the actual recipe part, that's going to be in the section that we call the experimental section. In the discussion section, that's where you're going to talk about, you know, why are you adding the baking soda? What does the baking soda do? You know, what's the purpose of that? Why are you adding sugar? You know, why are you adding it in these ratios? And so your discussion section talks about, okay, this is why we're adding this to this, and what's happening.
Is the rough draft for the known or the unknown?
No, the rough draft is for the previous. Is for the rough draft is for the synthesis of the chromium oxalate complex. So, for example, why are you adding oxalic acid and potassium oxalate? You know? Etc. And so you got to show the chemistry of what's happening. Right. So just try to think of what's going on in the synthesis and put it together in a discussion. Write it up and submit that as your rough draft. The other sections go a lot faster. You know, some people like to start with the abstract section because the abstract is a brief outline of the discussion, of the whole experiment pretty much. I really don't want you to focus on any of the other sections. Just focus on the discussion section. It's the most time-consuming one, the most difficult. If you have stuff already written for the other sections, I'll take a look at that. All right, we're going to have a couple of chemical reactions quizzes this week, but no exam. The exam for Chapter 17 is either going to be pushed to next week or the week after, depending on how long it takes to get through.
The reaction quiz, the last one we did, are we getting that back soon?
Yeah, you should be getting that back.
Was it better? Was it about the same?
Oh.
Worse?
No, it's better.
Okay, all right.
Should be better.
Okay.
For most people, yeah. I think. I mean, it's just a way to recoup some of the lost points. All right, any other questions? So we were talking about different mixtures. For example, HCl and sodium chloride. Right? HCl and sodium chloride, what's the most important thing about that mixture?
Salt.
Complete dissociation. And so the chloride, does that perturb the equilibrium at all? No, it's a one-way reaction. So this is the type of stuff you should be doing when you're going back through these. You know, give some kind of take-home message. You annotate your notes, write little notes on your notes saying, okay, this mixture is important because of this. Then we had the, what else do we have? We had HCl and acetic acid. What was your take-home message for HCl and acetic acid? The hydronium. The hydronium, what was significant about the hydronium? Yes, it's a common ion. That's true. What was the, I guess, a little bit surprising result of that calculation? Maybe
Water does kind of contribute towards the hydronium equilibrium.
in HCl and this, was it HCl and acetic acid? Yeah. Was that the most important thing that you got out of that problem, is that the water contributes hydronium? Is that? Sometimes it's hard to see right off, and so the ways to help you, look at, why are we covering this example in class, is to do it yourself, and then look at it. Sometimes the patterns aren't readily apparent, or what the point isn't readily apparent. A lot of times, I've tried different things, like put a take-home message on stuff, but a lot of people just memorize. They memorize it. It's like a recipe. You just memorize it, but you don't really need to think about it. You can memorize things without thinking about the significance of it. You just but the best thing is to leave it blank and then have you come up with what is the take-home, what's the most important thing from this particular problem. And so the most important thing from HCl and acetic acid is that hydronium from water contributes. Is that it? See, this is the type of stuff you want to have, before going into the test, because if you have little annotations for all these, then you can quickly go through and just reinforce those in your memory. And so you would reinforce hydronium from water is important when you're dealing with a strong acid and a weak acid, that kind of thing. And so you better keep an eye out for that. Sure? Was that did somebody else come up with a different important point for a strong acid and weak acid mixture like HCl and acetic acid?
Doesn't HCl contribute like the only significant hydronium, and the weak acid and the water don't contribute? It's a significant amount.
Yeah, that's an important point too. HCl is the main contributor, and it turns out acetic acid and water were negligible, even though normally we think of water as being negligible, but in this case, even the weak acid, and it was a big concentration, it was 0.100 molar acetic acid. 0.100 molar acetic acid normally has a pH around 4, in the 4s. And that didn't contribute at all, which is a bit unusual, And so I think for me that's the take-home message of that particular problem. If you have a weak acid and a strong acid, the strong acid completely dominates because of the common ion effect, right? And then we had some others. What were some of the others? Like a weak acid and a weak acid. The weak acid and the weak acid were, you have time. The chapter 17 test, which is, a lot of people say is the toughest, or one of the toughest, is not for a little bit, and so you have time to absorb, think about the material, make sure you understand it. But a weak acid and a weak base is what? A buffer, right? It's a buffer because the weak acid and weak base don't completely neutralize each other out. They exist in solution. And so when you have a stable solution that contains both acid and base, we call it a buffer. How would you solve that, the inventory of the pH of that particular weak acid, weak base? Simultaneous. That's good. And then what? We look at we looked at. You have a little bit of a reprieve because normally, test would be on Thursday. So, but even though you have a little bit of reprieve, you should still, imagine that the test is coming right up and you want to stay on top of the material. And so the next solution was also weak acid and weak base, but it was quite a bit different. What was different about it? Everybody finds their own method of what works for them as far as being successful or doing well on the test. I tried many methods because you get a lot of advice. I talked about this on the first week. So I think I tried. Well, every piece of advice that was given to me, I tried it, just to see if it worked for me. And so you just try different things until you find something that clicks well. And so just try it. Try reviewing your notes more frequently. That's, I think, one of the big things if you could do that. But, it's not just reviewing. It's also the analyzing part, because reviewing is just kind of like rote memorization. And that really doesn't have much impact, I think. And what's much better is to annotate them and put down, this is important because of this, or highlight certain things. And so the next mixture, what do you have? Or what's unusual about it, or what's important about it, or what do you have for that?
It was the acid and the base that's amphoteric.
Yeah, it's the amphoteric. So the acid and base are the the same thing.
Yeah.
And so what was the important point about that? Do we do the Ka or the Kb? Or were they redundant? Were the Ka and the Kb redundant?
They weren't redundant.
They weren't redundant. And you have to do you have to do both. And not only that, K and Kb, but also how they tied together. This happened with the HCl and the ammonia. Not HCl, acetic acid and ammonia. Same thing happened there. K and Kb have to be done, but they're tied together with Kw. Right? So simultaneous three equations. I talked about three equations. Do you think three equations is going to be easy to solve simultaneously? Because what has to happen is the hydronium has to match with the Ka and Kw. The hydroxide has to match with Kb and Kw. And the hydronium, actually, and the, bicarbonate has to match with Ka and Kb. You think that's easy to do? No. And so tell me what happened. The reason I'm bringing this up is because I often get asked, how can I do well in this class? I'm studying quite hard. But, I was studying really hard for my classes too, but I wasn't doing well when I first started. It's because of how I was studying. You could put in all your free time into studying and still not do well if you aren't, And so this is why this is the method that I used to study. The method that I used to study that I found effective was to go back through my notes and then have a little take-home message for everything, you know, in the notes. And that made it more memorable for me. I don't always write the take-home message, and most of the time I don't, because I leave that up to you. I'll say it, you know, verbally, but I don't write it on the board. It is up to you to come up with that. And so we had the bicarbonate, and the take-home message of that was, it's simultaneous, just like the ammonia and acetic acid, but what? Unlike the acetic acid and ammonia, what did I say about solving the simultaneous for acetic acid and ammonia? Are you going to be responsible for that?
No.
No. What about for bicarbonate?
We are responsible.
You are responsible. And so what's the difference? Why are you responsible for one and not responsible for the other? Can somebody explain that to me? Both involve simultaneous with Ka, Kb, and Kw. But one doesn't work, the other works. Why? You know, this is the type of stuff. This type of stuff you don't notice. You know, if you just go through it once, you don't think about these things. But when you go through it multiple times, you go, wow, isn't that the same as this? And yet we have to solve this way, but the previous one we don't. Why can't we just solve it the exact same way?
Because the acid and the base coexist in the...
Well, but they both coexist. The acid and base coexist in both solutions. Yeah. Well, did I say conjugates, or the acid and base are not conjugates of each other in bicarbonate. The acid and base are the same thing, and therefore the math can be simplified. Whereas in ammonia and acetic acid, the acid and base are not related, and therefore cannot be so simplified. You know. So anyway, for that, I think, you know, these types of steps were the most effective for me. You know, for improving my scores, doing this type of stuff, going back through my notes. And you know, over the weekend, I wouldn't have let them sit and then come back to them over the weekend, because, you know, they say your memory exponentially decreases. You know, the next day you've forgotten this much, but you know, over the weekend it's all gone. You know, your short-term memory. You know, so I tried to do it ASAP, so my you know, because something said verbally but not written on the board is difficult to catch. But sometimes you'll remember it, you know, and then you can write it in your annotations. Okay. So my suggestions. So try it, or try other ways. There are lots of books written on this subject. Okay, so we had that. Now we have the next buffer solution, and the next buffer solution is very special because they are conjugates, right? And that is the acetic acid and sodium acetate. And so we came up with the equation. What was the equation? The name?
Henderson-Hasselbalch?
Yeah, the Henderson-Hasselbalch. And so what's the big deal about the Henderson-Hasselbalch? Somebody asks you, what's important about the Henderson-Hasselbalch? What would you tell them?
It's only for the conjugates.
Yeah, it works only for conjugates. That's important.
Simplifies solving for pH.
It simplifies solving for pH. How so? How does it simplify it?
It helps you skip the ice treatment.
Yes, the biggest advantage for the Henderson-Hasselbalch is skipping the ice table. And so we did the calculation. We did the calculation with the ice table, and we did the calculation with the Henderson-Hasselbalch. Is that correct?
Yeah.
The Henderson-Hasselbalch was way easier, wasn't it?
Yeah.
Okay. It was way easier. What were some of the assumptions that you have to make in using the Henderson-Hasselbalch?
That the initial concentration wouldn't change significantly.
Okay, so the one of the assumptions is the simplifying assumption works.
Yeah.
Simplifying assumption should work because you have, what was that? It's a weak acid one and
Yeah, a large concentration.
a product, yeah, initial product, good. And so the common ion effect. Right? And what else? Was that it? Yeah, K is small, so it only works for weak acids. So any weak acid, it should work. You know, okay. For strong acid, it's not going to work at all. The strong acids are pretty much one-way reactions. Common ion effect is not important in strong acids. The other assumption that was made for the Henderson-Hasselbalch is you need significant concentrations of the acid-base conjugate pair. Because let's say you had micromolar. If you had micromolar acetic acid and micromolar sodium acetate, it's so dilute, the pH should be close to 7. And so if you had micromolar stuff, then could you use the Henderson-Hasselbalch? No, because that's going to give you a pH of 4.24. And so you would have to instead use the ice table. Figure it out. But unlike you know, these types of things you go through after going through it many times. But unlike amphoterics, you know, because if you have acetic acid, it's Ka for this, and you have acetate, there's a Kb for this. And so there's a Ka and a Kb collision we have to worry about. One generates hydronium, the other generates hydroxide. But how does this compare to amphoterics? You know, in what way are they alike? Well, they're alike because they both have Ka and Kb collisions. In what way are they different? There's a Ka for bicarbonate and Kb for bicarbonate. We talked about this. So in what way are they alike? Well, that's how they're alike. In what way are they different?
One's an acid in its conjugate phase, while the other is the exact same molecule.
Yeah. Yeah, that's critical. Okay, anything else that's important? Did everybody catch that? This is conjugates. Over here, the acid and base. Over there, they're the exact same. And so what's the take-home message? So what? So what difference does it make in how you solve the problem?
It makes a difference because you have to account for more variables.
With which one?
With HCO3 bicarbonate.
Okay, you have to account for more variables, like?
The HCO3 concentration, the OH concentration, H3O plus.
Okay, so you're saying we have to account for all of it, the Ka, the Kb.
And how they affect each other.
Why don't we have to do that for the other one?
Because with the acid and its conjugate base, we can just use the Henderson-Hasselbalch just when each of them reverts into the hydronium.
We could use the Henderson-Hasselbalch, but you know that answer is fine. You're correct, but it really doesn't get to the nuts and bolts of why. I mean, there's something else. There's one important message here, because
The change in concentration isn't significant anymore. That it would affect the acid.
Okay. Okay, those are all, those are all valid points. Those are all good. But I need to step back a little bit. So Henderson-Hasselbalch is based on Ka, right? Henderson-Hasselbalch. What happened with the Kb? Over here, we have to do both Ka and Kb. Henderson-Hasselbalch consists with the Ka. What happened to the Kb? Did I derive the Henderson-Hasselbalch already? Yeah, we did the derivation, and it was only the Ka collision, right? What happened to the Kb collision? Maybe I'm not done. Maybe I only made it halfway through because I forgot or I skipped Kb. If somebody asks you, well, what are you doing with the Kb? You're completely ignoring it. I have 0.100 molar acetate. That's a huge amount of base. What are you doing with it? Oh, huge in relative terms because, the acetic acid is 0.100 molar. And so somebody comes up and asks you, what are you doing with the Kb? You completely ignored it. You're wrong. You should do it like this. Simultaneous. Then you tell them
It'd be redundant.
it'd be redundant, right? And so here, that's good. That's the point. The point of this is, the different because this is redundant, but isn't this redundant? How can you tell if this is redundant and this is not redundant? How can you tell? How did you know that? Did somebody just tell you that this is not redundant and you memorize it? Is that how you're studying for this class? Because if you're studying that way, then it's not going to work successfully. If you're just memorizing, okay, this is redundant, this is not redundant. Because it's so easy to get it mixed up unless you drill it. If you're like Mr. Flashcards or Miss Flashcards and you're just doing it over and over and 1,000 times. This is redundant, that's not redundant, this is redundant, that's not redundant. But that's only going to get you this far. Because if you get a new problem, then you're out of luck. Because you didn't have it memorized. And so, how can you tell when something's redundant and something's not redundant? We did it 2 or 3 times in class. How can you tell? And it should, you should, from the first time we looked at redundancy, which was back when we were doing step 1, step 2, step 3 for phosphoric acid, that should have already been drilled down, like that. So how can one tell if it's redundant or not redundant? Because what did we say? This was redundant or not redundant?
Not redundant.
And this is redundant. And both are Ka and Kb collisions. And so some people go, oh, I just memorize it. If it's conjugate, it's redundant. If it's not conjugate, it's not redundant. Is that the way to do it? You could. If you want. If you can write a little annotation like that. Conjugates, redundant. Not conjugates, not redundant. And then you have that annotation, and then you could just memorize it. But that's not the way we did it back when we were doing phosphoric acid. Back when we were doing phosphoric acid, how did we determine if it was redundant or not redundant?
Because the opposite reaction, well, when you did Ka, you found pH, and then doing Kb, you find the same thing, but only in terms of pH.
Okay. Yeah, that's right. That's correct. And so you just write it out. If it describes the same equilibrium, right, then it's redundant. And so let's follow up with that here. And so we'll do the Henderson-Hasselbalch. Based on Kb. If we did this, we'd start off with the acetate, and then we'll do Kb collision. Kb collision is going to generate acetic acid and hydroxide. The way we did this, if you go back in your notes, the way we determined that this was redundant is because Ka describes the equilibrium. This is the words I always say when talking about redundancy. And you could describe it. The best is to describe it in your own words. But at least if you don't describe it in your own words, then just repeat somebody else's words for it. The way I said this is that Ka describes the equilibrium between acetic acid and acetate in terms of hydronium, whereas Kb describes the equilibrium between acetic acid and acetate in terms of hydroxide. And so the only difference is pH and pOH, right? And this is why for the Henderson-Hasselbalch, the other point is the Henderson-Hasselbalch, we use Ka because, why do we use Ka? We use Ka because it's just more convenient. That way we don't have to calculate the pOH and then convert it to a pH, because normally we talk in terms of pHs instead of pOHs. Kb is going to generate a pOH. So we would go through the whole derivation. You could work this derivation out. You know, we get the Kb, we fill it in, and eventually we'll get the Henderson-Hasselbalch based on the Kb equation, which is going to be the pOH is equal to the pKb plus the log of the acid over base initial, assuming the simplifying assumption worked. And so not only is this less convenient because we're getting pOHs, this is also less convenient because we have to use pKbs. Are pKbs typically found, or Kbs found in the table? No, we usually have to calculate the Kb based on the Ka of its conjugate acid. And so using Henderson-Hasselbalch in this form, even though we get the same answer, is just less convenient. But shouldn't we use the base form of the Henderson-Hasselbalch if the base is the dominant species? Because back here we saw that the Ka was much bigger than the Kb, right? For acetic acid, Ka is 10 to the minus 5. The Kb was more like 10 to the minus 10, roughly. And so the Ka was dominant, so it just seems right to use the Henderson-Hasselbalch based on the Ka. But what if you have this? What if you have 0.100 molar ammonia and 0.100 molar ammonium chloride? Well, the base here is going to be ammonia, and its conjugate acid is ammonium. And so this would be the conjugate pair, base and acid. The Ka for ammonium is given on the chart here. The Ka for ammonium is 5.7 times 10 to the minus 10. And therefore, the Kb for ammonia should be Kw divided by the Ka for its conjugate acid. What's the conjugate acid of ammonia? NH4 plus. So this would be the Ka for ammonia, which is 1.0 times 10 to the minus 14 divided by 5.7 times 10 to the minus 10, which gives us a Kb of
17.54 times 10 to the negative 6.
Okay, I'm going to change that to 1.75 times 10 to the negative 5. So which one is the dominant collision? The Kb collision or the Ka collision? Kb, so we're going to generate more hydroxide than hydronium. If we have more hydroxide than hydronium, this solution should be basic. If the solution's basic, can we still use the Henderson-Hasselbalch for acid, Ka, pH? Yeah, we can. We have a choice. We could either use the pOH equation or we could use the pH equation. Does it matter?
Yes. One's faster,
Well-
maybe.
Yeah, one's faster. But ultimately, I should get the same answer either way. And there's one other subtle difference, which we're going to talk about in this problem. The subtle difference is a lot of sharp students will pick it up that, hey, wait a minute, there's something wrong about this particular problem. Maybe. And so why don't you go ahead and solve for the pH of this using either equation. If you get the pOH, then you have to do this extra step, 14 minus the pOH to get the pH. We have the Kb and the Ka value, so it's not going to be that huge of a difference between the two methods. Somebody have the answer? Should take about this long because the Henderson-Hasselbalch is a huge time saver.
Is it 4.756? No. Okay.
Did you do the pOH?
No.
Most people have this equation memorized because they use it so many times. You know, pH is equal to pKa plus the log of base, which is ammonia, to acid, which is ammonium. And here, are we going to bother with the ice table? No. And so this is going to be 0.100, this is going to be 0.100 because the change, you know, the plus x and the minus x, or minus x plus x, is going to be so small. It's going to be negligible. So this is just, pH is just equal to pKa. This goes to 0. pKa is the negative log of the Ka, which is
7.6.
9.244? Is that what it is? Okay. I don't want to round it. It came out 9.243? 244, okay. Good. Do you see how quick that calculation is? Less than a minute you should have the pH for this buffer. And so that's a big advantage of the Henderson-Hasselbalch. But there's one other thing that we assumed about the Henderson-Hasselbalch. The other thing that we had assumed about the Henderson-Hasselbalch is, one, you know, the change, the x's are so small that we can go ahead and use the initial, right? And we need significant concentrations of both, which we have, 0.100 and 0.100. But there was one more thing that we assumed in the Henderson-Hasselbalch, and what was that? has to do with KW. Yeah, the hydronium from water is negligible. And so, is hydronium from water negligible in this case? That is KW significant? And so what is the hydronium concentration roughly? We have about a pH of 9.24 is a hydronium concentration about 10 to the minus 9, 10, right? Something like that. Molar hydronium. If we have 10 to the minus 9 molar hydronium, is the hydronium from water significant? 10 to the minus 9 molar hydronium. Is the water from going to be a significant contributor?
Yes.
Remember this? You guys remember the 1 times 10 to the minus 8 molar HCl? What was the pH of that?
Like 6
Yeah, it's close to 7, right? Why wasn't the pH 8? Shouldn't this be 10 to the minus 8 molar hydronium, pretty much? So this should be pH 8.
That's not taking into account the hydronium concentration from water, which would be significant at such low molarity.
Yeah, when we have a very small molarity of hydronium, then water is going to be an important contributor, right? And what did we say is a small molarity of hydronium? Well, you know, how much can water contribute? Do you guys remember? Roughly. What's the maximum amount of hydronium water can contribute? 10 to the negative 7 would be the max, but it's like 10 to the negative 8, 10 to the negative 9, it would contribute, right?
Yeah.
Well, we got 10 to the minus 9 molar hydronium here. Is water going to be a significant contributor to the hydronium in this problem?
Yes.
I mean, if we have a minuscule amount of hydronium, then you would expect, yeah, water should add a significant amount to this, right? Because if I had 1 times 10 to the minus 9 molar HCl, I'm not going to expect a pH of 9. No way, because when I got 10 to the minus 9 molar hydronium, I'm going to expect that water will be a significant hydronium ion contributor based on what we did at the beginning of chapter 16. Right? So that was the take-home message from that problem. Very, very low concentrations of acids, we're going to have water as a significant contributor. So we have very, very low concentration of acid, then water must be a significant contributor of hydronium. Does that make sense? Do I have to, that means I can't use the Henderson-Hasselbalch. I need to use the ice table, right?
Correct.
Yeah, that all seems to make sense, but it turns out that water is not significant. Is KW significant? The answer is no. So tell me why KW is not significant here, but it's significant here. I mean, I'm contradicting myself, right? Or am I? Because earlier I told you to worry about it. Now I'm telling you not to. Why the...
Our initial concentrations are large.
Initial concentrations are large, yeah. But that doesn't mean anything because the hydronium is small. Hydronium small. Remember the What's important is, does step 2 perturb step 1? If you were to do step 2 here and figure out how much additional hydronium we'd get, it would perturb it. Right or wrong? So take a minute and think about the difference between this, why I'm saying we could ignore it here, but we couldn't ignore it before.
Basic solution.
Yeah. It's because it's a basic solution. This is a basic solution. Why am I looking at hydronium? You know, remember the old rule we had is in basic solutions you look for what contributors? Hydroxide contributors. And so if you have a basic solution, are you going to be worrying about the hydronium? No, you worry about the hydroxide, and you worry about, will Kw be a significant contributor to hydroxide, not hydronium, because hydroxide actually, if you have 10 to the minus 9 molar hydronium, what's a hydroxide? A lot higher. Well, they have to add up to 10 to the minus 14. So minus 9 plus minus 5. So that means the hydroxide must be roughly 10 to the minus 5 molar. If you have hydroxide at 10 to the minus 5 molar, will Kw be a significant contributor to hydroxide? No. 10 to the minus 5, the most you're going to get is like 10 to the minus 8, 10 to the minus 9. Something like that. And so here we're looking at it wrong. The reason we're looking at it wrong is because we want convenience. We want to use the Ka, even though the Kb is dominant here. You know, really we should be using the Kb because the Kb is the most important collision, right? And then when we do the Kb, then we should ask, is Kw a significant contributor? But we didn't do the Kb because we wanted to save that extra step. So do you see that they'll give you the same answer, but you know there's one trick to it, and that one trick is that if we're using the Ka for everything, then when it comes to seeing if Kw is significant or not significant, we got to look. Is it an acidic solution? If it's acidic, we're looking at the Kw contribution to hydronium. Or is it a basic solution? If it's a basic solution, then we're looking at the Kw contribution to hydroxide. Well, the hydroxide here should be about 10 to the minus 5, which means Kw is a insignificant contributor. And so we'll just continue using the acid form of the Henderson-Hasselbalch equation with that realization. Okay. So if I change the ratio, what's that going to do? You know, let's say if I add more base or if I add more acid, what's that going to do to the pH? Well, if I add more base, the pH should go up. If I add more acid, then this becomes more negative and the pH should go down. And so we could calculate, you know, these changes quite rapidly. So for example, if I had 0.200 molar ammonia and 0.100 molar ammonium from ammonium chloride. I'll just add some ammonium chloride. Ammonium chloride is what we call a strong base. Is ammonium chloride a strong base?
Salt.
Ammonium chloride, does it dissociate completely? Well, it's not a base. It must be a strong acid. Strong acids dissociate completely, right? So is ammonium chloride a strong acid because it dissociates completely? Or it's a soluble salt. Soluble salts also dissociate. So ammonium chloride is a soluble salt. Skip that step and just go straight to the ammonium here. rather than calling it ammonium chloride. Chloride's still there, but it's a spectator. So go ahead and tell me the pH. The pH is equal to pKa plus log of the ratio, base to acid ratio. What's the log of that ratio? Log of 2. So one up about 0.3, so the new pH comes out to 9.545. So if we double the ammonia, we expect a little higher pH. Now we double the base, but the pH really didn't double, anything like that. It just went up a little bit. And so what we can do by adjusting this ratio is we can adjust the pH up or down. And so this means that I can have a target pH, something I might want. Let's say I want a pH of 9.00. So we want a pH 9.00 buffer. All I have to do is just add a little bit more ammonium to this. If I add a little bit more ammonium, then that's going to drop the pH down, 9.00. And so what we'll have here is we can use ammonia, ammonium, this conjugate pair. And so the pH, desired pH is 9.00. The pKa is 9.244 plus the log of the base ammonium to acid ammonium ratio. And so just rearranging this, I'll get minus 0.24, subtract 9.24 from both sides, is equal to the log of the ratio here. And then just raise everything to, or take the anti-log of this. 10 to the minus 0.24 is going to equal the ratio of ammonia to ammonia. And so what does the ratio come out to? How many sig figs are we now? 3. We should actually have 3 in the concentration because of the concentrations at 3 sig figs a day.
0.575.
But in this case, we only have 2, so 0.5775. That's the ratio. And so what this means is this. We could have 0.575 molar ammonia and 1.00 molar ammonium. And so if we make a solution that is 0.575 molar initial ammonia and 1 molar ammonium chloride, then it should work. It should give us a pH of 9. We can make things more concentrated. You know, what if I make this 5.75 molar ammonia and 10.0 molar ammonium? Will this have the same pH? Yeah, this will have the same pH. Or I can make it more dilute. This is going to be more expensive. It's more expensive because you need more solute. If I make it more dilute, I can go, let's say, 0.0575 and 0.0100. And this should have the same pH. But I have to worry, if I get too dilute, what will happen?
It hydronium concentration from water.
Yeah, water is going to be the most significant contributor. And if water is the most significant contributor, the pH should be close to 7. And so we need significant concentrations of both. And so at some point, you have to quit using the Henderson-Hasselbalch and switch to the ice table. We can also invert this. If we invert this, what does it come out to? Invert it. And so I want 1.00 molar ammonia on the top and what on the bottom? And so if I mix this, it should come out pH 9 too. And so sometimes I'll invert it. Or anything, you know, you can pick whatever concentration. As long as it comes out to that ratio, we're good. 9.00. So that works pretty good. Let's do another example. All right. I want a let's go with a pH 2.00 buffer. Use ammonium. All right, so tell me what the ratio is going to come out to. To get that low of pH, I'm going to need a lot of ammonium acid.
It's 5.701 times 10 to the negative 8. NH3 over NH4.
All right, the base to acid ratio comes out to 5.701 times 10 to the minus 8, which means that we need 0.1, 2, 3, 4, 5, 6, 7. Ammonia. Something like that. How easy is it going to make? How easy will it be to make this ammonia solution? That's going to be hard, right? To measure out that little bit. So let's just move the decimal over. Make it a little easier. Let's make this. If we just go like say 0.570 molar ammonia, half a molar ammonia shouldn't be difficult to make. So if we want 0.570 molar ammonia, then what would we make the ammonium? 1, 2, 3, 4, 5, 6, 7 zeros. This should give us a pH of 2. It's going to be expensive, and then there's one other problem with this, and it's solubility. You know, solubility is defined as the maximum amount of solute. You know, can we jam that many grams of ammonium chloride in a liter? 10 million moles of ammonium chloride in a liter isn't going to fit. It's impossible. And so, even though the pH should be good, you know, here, there's a major problem with this buffer. What is the major problem? A buffer should have what? Significant quantities of both acid and conjugate base. And so, as an aside here, the problem is with capacity. And I'll talk about that in a second. So here, you know, I could have conjugate base and acid present if I look at just 0.100 molar acetic acid. And so if we do this as an aside here, if I have 0.100 molar acetic acid, don't I have acetate present? You know, I could save money. I'm going to save money. I'm not going to add any sodium acetate. So I don't have to buy any sodium acetate to add to this, because you know what I'm going to argue? I'm going to make some acetate anyway, right? Because if I have just acetic acid present, then there's going to be a Ka collision generating my acetate, thereby saving me lots of money. And so I'll go 0.100 molar and 0 and 0. And then, you know what? At the end, I'm going to have some. I'll have some acetate at the end. This is going to be X molar acetate. This is X molar. This is going to be 0.100 minus X. Is this a buffer? I have acid, I have its conjugate base. That's a buffer. Right? The acid and base coexist at equilibrium. The acid and base coexist at equilibrium. This is a Henderson-Hasselbalch buffer, isn't it? I've seen this in fact. People will try to use it. You know, pH is equal to pKa plus the log the base, which is 0, and the acid, which is 0.100. Just use the initials. What is the log of 0? 1?
Log of 0 is it's not a log.
Undefined? Log of 0 is undefined. Means infinity? Negative infinity?
Well, maybe it's approaching 0, but
Approaching 0?
right, no, it's not. It's not. Approaching infinity.
What's the problem with this? Yeah. We don't use this here. We call this an acid solution. We do not call this a buffer solution. Why don't we call this a buffer solution?
Because we have no concentration of acetic.
Yeah, we have no significant concentration of acetate. We're going to end up with a tiny amount at equilibrium, but this tiny amount is not enough to call it a buffer. Well, the same type of thing happens here. You know, this is almost just like a ammonium solution because there's so little ammonia present. And so this is the problem with this. A buffer should have significant quantities of both acid and base, or base and acid here, but here we have an insignificant quantity of base. To make it a significant quantity, you know, we'd be exceeding the solubility of ammonium. It would be ridiculous. In other words, it would be way too lopsided. And so this has lots of acid, no base. And that doesn't make a good buffer. So there's a limited range in which you want to adjust this, you know, because you don't want the ratios to go too out of control. And so the best pH, which we call the optimum pH, is when you have a 1-to-1, you know, acid and base, like 0.100 molar ammonium, 0.100 molar ammonium. That's optimum. And so, in other words, there's a limited range because we don't want overcapacity in one and undercapacity in another. We want, you know, as close to equal capacity as possible. And so to keep it within the range, we usually go like this. You know, if we have a 1-to-10 ratio of base to acid, then what is the log of 1/10 versus a 1-to-1 ratio versus a 10-to-1? We try to keep things within a 10-to-1, 1-to-10 ratio. Here. Because when we have a 1-to-1, this is the optimum pH. Optimum pH because it has equal amounts of acid and base. Here. And so the optimum pH is equal to the pKa because the log of 1 is 0. And so the pH is just equal to the pKa. We don't really want to get more than 10 parts of base to every part of acid because then it's lopsided. This is starting to resemble a base solution rather than a buffer solution. And so here we have the pH is equal to the pKa plus the log. Actually, do that below. It's just pKa plus 1. Because over here the pH is equal to pKa plus the log of 10 to 1. And over here, you know, if we get 10 parts of acid to every 1 part, then the pH is equal to the pKa minus 1. And so the range that you can adjust the pH for practical purposes is the pH is equal to the pKa plus or minus 1. And so we'll say the range over which the pH can be adjusted and still have a useful buffer. Not lopsided, useful buffer. Does that make sense?
So the most you can have is a 10-to-1 ratio. Either way.
Yeah, either way, 10-to-1 ratio. Because it's not that you can't go beyond it. You can go beyond it, but if you go beyond it, then when do we stop calling it you know, it's going to be dominated by one species or the other. So when we want a pH of 2, then we should find an acid with a pKa of 2. If we can find an acid with a pKa of 2, then that's perfect, or pKa close to 2. And so we shouldn't have been using ammonium because the pKa of ammonium is 9.24. It's too far away from 2. And so let's do another example here. This example is, let's say I want the buffer with pH equal to 7.00. If I want a buffer with a pH of 7.00, then I want to find an acid that has a pKa of 7.00. Now we're in luck because there is an acid that exists with a pKa of 7.00. That's H2S. H2S has a pKa equal to 7.00, right on. And so that means I just have to mix H2S and its conjugate base. What's the conjugate base of H2S? HS minus in a 1-to-1 ratio. If I mix those in a 1-to-1 ratio, then the pH is equal to pKa plus the log of the ratio. The log of the ratio is 0, so the pH is just equal to the pKa. And so H2S is the perfect acid for this. Or it appears to be the perfect acid for this, but it isn't. What are the problems with using H2S? There are multiple problems with using H2S. One is it's a gas. And so let's say you need to weigh out, if you need to weigh out 1.0 grams of H2S, how do you do? How do you weigh out 1.0 grams of H2S gas? I guess you could liquefy it, but you got to worry about evaporation. So rather than liquefy, you got to freeze it into a block, and then get out your chisel and hammer and chip off pieces of the block until you get 1.0 grams. I guess you could stick a tube in a beaker and just start bubbling it. But if you start bubbling in a tube, you know, most of it will bubble out, right? But I guess you could watch the mass of that on a balance. Yeah, you could do calculations. You know, get a balloon of it. You get a balloon of it, PV equals nRT, you know, figure it out. And then take the balloon and then submerge it into your beaker and then pop it and let all the H2S absorb into the water. But do you think all the H2S is going to absorb into the... No, it's going to bubble out, right? And so H2S is a gas, and it's difficult to work with gases, so it's not going to be very practical. But there's another problem. H2S, if it bubbles out, you know, you're going to have a headache because the stuff smells like rotten eggs. In fact, that's what rotten eggs emit, H2S. Or you could potentially die because H2S is very toxic. And so we don't want to work with H2S. Even though it has a perfect pKa, it's not very practical. And so look for a compromise. So H2S has a pKa of 7, which means its Ka is 10 to the minus 7. And so we're looking for an acid with a Ka close to 10 to the minus 7. Do you see one? HSO3 minus. So we could use bisulfite ion, HSO3 minus. We mix that with what? HSO3 minus and H2SO3. So we mix HSO3 minus with H2SO3 and get a buffer that way? No, not with H2SO3. We'd have to mix it with sulfite. Yeah, SO3 2 minus. Right? Because if we mix it with H2SO3, then H2SO3 would be the acid and HSO3 would be the base. And so we got to take HSO3 minus and mix it with SO3 2 minus, and that would be the acid base. That's one choice. What's another choice? Are there any other choices?
H2CO3 with the CO2 plus H2O.
Yeah, H2CO3 is the trouble. Because if you went to the chemical reagent store and tried to buy a bottle of that, could you?
You get put on the list.
It's not on the list of. They could try to make it, but what's going to happen to H2CO3? Yeah, it's just going to bubble out. And so immediately when you open the cap, it's like a carbonated beverage. All the CO2 gas is just going to evolve out. Any other choices?
Is it water?
Water is good.
Pure water.
Water is great. There's a base and acid that coexist. Except water is a little trickier because we don't call it a buffer. We'll talk about that water in just a minute.
Could you maybe like dilute one of the solutions or something to make it pH 7?
Yeah, we could take anything and dilute it down enough. But the reason we don't want to do that is because of how buffers work and why we want high concentrations of acid and base in there. The reason we want that in there is to neutralize any strong acids or strong bases that are added to that solution. So we're going to do an example of that later, but we need significant concentrations. Now, if we make it dilute, like micromolar and micromolar, then it's close to pure water. Pure water is what we call unbuffered. And I'll show an example of that in a minute. But the other thing that might work is H2PO4 minus. Do you see H2PO4 minus as a Ka close to 10 to minus 7? And so let's use H2PO4 minus. I want to get the pKa value from the book. The pKa value for H2PO4 minus is 7.20. You see, that's close. All we have to do is add a little bit more acid or a little bit more base from 1 to 1. If we had a 1 to 1 ratio, then this would be the pH. And so I need to adjust the ratio a little bit by adding more what? Acid. Yeah, I want to drop pH. And so here I say, well, is this my acid or is this my base? This is my acid, and therefore what is the base?
HPO4 2 minus.
Yeah, HPO4 2 minus must be the base. And so I need to add a little bit more HPO4 2 minus than H2PO4 minus. And so the desired pH is 7.00, which is equal to the pKa plus the log of the base, which is HPO4 2 minus, initial to the acid, H2PO4 minus initial. One thing is hey, aren't these both amphoteric? This is, hey, wait a minute. Because I'm just calling this acid. What happens to Kb? Can I turn off that collision? If I'm calling that my acid, then that's the Ka, and what about the Kb collision for H2PO4 minus?
Well, since we're going to pH of 2, that means that the pH is going to be like 12, which means that the hydroxide is going to be very small, so it's going to be almost like a guess you can also again say it's like it's a negligible equation.
Okay.
I guess
Hmm. The hydroxide is going to be small, therefore we can ignore it. You guys agree?
no.
Hydroxide is going to be small, therefore we can ignore it. This is an amphoteric ion. Didn't I just get done talking about amphoterics? Amphoterics, we need the Ka and the
KB.
Kb. And both. So what does that mean? Simultaneous, which means that I shouldn't be using Henderson-Hasselbalch. I should be using that other equation that we did, right? This is amphoteric. This is amphoteric. So I just got to use that equation. pH is equal to the pKa of the conjugate and pKa and the amphoteric divided by 2. Remember that equation? So I use that two times. Yeah. Yes? No. What gives me the right to call that just an acid and not an acid and a base? I guess like what we were saying, maybe the hydroxide is so small we don't really care about it. I mean, if this is the pKa of this, let's just do this as an aside over here. Aside. We have H2PO4 minus. The pKa is 7.20, therefore the pKb is 6.80. True or false? This is the pKa and the pKb have to add up to pKw, 14. So true or false? False? This is like typical multiple choice question. True or false? I'm going to start throwing some true or false multiple choice on there. 50-50. What's your, oh man, this is a test. What are you going to select? True or false?
True. I would say true.
Answer is false. Why is the answer false? Somebody tell me why the answer is false.
The logs, because we're neglecting the logs.
Well, the power function already incorporates the log, so we don't actually have to worry about the logs. It's false for another reason. It's false because these are little details you don't notice the first time you go through, but by the 50th time you look through them, you see it.
Because the pKa and the pKb are different at equilibrium.
They're going to different. The pKa for H2PO4 would turn into H3PO4.
Not H3PO. I forgot to cover this in the morning. Why is this false? You know, because the pKa plus the pKb should be equal to the pKw. I know the pKw is 14.00. This is a simple addition. So 680 plus 720 should give me 14. This is a little subtle thing. This is a subtle thing when you're dealing with amphoterics. It automatically clicks or you don't see it.
Isn't the conjugate different?
Yes, that's the reason. This equation only works for conjugates. We're not dealing with conjugates here. We're dealing with the same species. And so the PKB, yes, this is true, but I would have to use the PKB for what? Not for H2PO4 minus. Yeah, if I rewrote this like this, then it's true. Let me rewrite it so it's true. This would be the pKa for H2PO4 minus is 7.20, and the pKb is 6.80 for HPO4 2 minus. Then it's true. Right? But it can't be the same thing. And so what is the pKb for H2PO4 minus? I need to know the pKb's to see if I can ignore it. And so just redoing this, the H2PO4 minus has a pKa of 7.20 and a pKb of well, the pKb is going to be equal to 14.00 minus the pKa of what acid? H3PO4. What is the pKa of H3PO4? We could look that up in the book. So 14, and does somebody have their book? Well, I'll just go from memory. 2.15. And so this is going to be 11.85. Oh, so maybe you're right, because if the K is around 10 to the minus 7 and the KB is around 10 to the minus 12, then right? Then maybe we could ignore the KB. Yes? Too many questions, too much confusion, right? Yeah. Maybe that's why I didn't ask this in the morning. I didn't ask this, but I do ask this on eventually. Are we done? Oh, sorry. So I'll leave you with a state of fog.